Now we are live.
Okay,
Nirupma.
okay, we are live, so I will start. Good evening, everyone.
Wait, Nirupma, wait. Okay, am I audible, Nirupma?
Yes, sir, you are
Yes.
audible. Should I start?
Okay, sir has joined, na?
Yeah.
Yes.
Yeah, I'm here.
Sir, good evening.
Good evening.
Okay, sir, thanks for your vital time. Okay, Nirupma, go ahead, please.
Okay, sir, thank you so much. Good evening, everyone. I once again welcome all the participants to the second session of the program, and I'm sure you're excited for the second program as well, as you already had an enriching session in the previous program, the previous session. So it's a matter of honor to introduce our next distinguished speaker for the day. He's a big name in the field of cognitive neuroscience and cognitive psychology. And sir, on behalf of all the participants and the organizing committee, I express my immense gratitude to you for accepting our invitation to deliver a lecture on cognitive psychology. Welcome, sir. Professor Narayan Srinivasan is a professor at IIT Kanpur. Sir completed his undergraduate degree in physics from University of Madras and obtained master degree in electrical engineering from Indian Institute of Science, specializing in biosignal processing. Sir joined the doctoral program Cognitive Psychology at University of Georgia, USA, 1992, and did his doctoral work with Dr. James Brown, and investigated the interaction between attention and spatial frequency processing mechanism. Sir also did his postdoctoral work at University of Louisville with Dr. Edward Essock and on diagnostic algorithms in glaucoma. Before joining CBCS, he worked at the Biomechanical Engineering Research Center at Nanyang Technological University, Singapore, and joined Center of Behavioral and Cognitive Sciences in 2003, University of Allahabad. At CBCS, Sir has used multiple approaches to study mental processes and have wide-ranging interest in cognitive science, along with various projects in different areas of cognitive science. So, sir, once again, I welcome you and thank you so much for accepting our invitation. Over to you, sir.
Thanks a lot. Thanks to Dharmendra and thanks to everybody here, including the audience. This is a difficult time to listen to a lecture. So I hope you will enjoy it and get something out of it. So let me share screen. Okay, can you see the slides?
Yes.
Yes.
Okay. So I'm going to focus a little bit on some of the work that I have done on the relationship between attention and consciousness. But before I do that, I thought it may be interesting or important to kind of tell exactly what is cognitive psychology or cognitive science, in the sense exactly how we approach understanding a particular mental process or interactions between different mental processes. So the methodology is important to understand any particular aspect of mind that we are interested in. So what I'm going to do is give some kind of a brief introduction. Some of it may be familiar to some of you or all of you, but thought it may be useful to start with that. Please, I don't know whether people will ask questions at the end or people will be allowed to ask questions in between. But if it is possible, if you don't understand something, I personally don't have any problem if you stop, but I'm not sure exactly how it will work here. Okay, so given that, let's move on. This is something that all of you are familiar. You may have opened a cognitive psychology textbook. This is a book for, Sternberg and Sternberg. And you may have heard of this word information processing approach. And this is essentially one of the important approaches that is available to study cognition. And essentially, you will see something like this, right? So this figure at the top shows a particular model of memory. And this is Atkinson and Schifrin's model of memory. Essentially, you have some environmental input. This is processed by various registers, which are modality specific. So you have visual, auditory, and haptic. Then the information goes to something like what we call short-term memory, and information goes back and forth between short-term memory and long-term memory. And of course, there is a response. Now, one of the things immediately you realize in this, from a structural point of view, is that there are arrows connecting these boxes, and these arrows are not arbitrary, right? So for example, there is short-term memory interacts with long-term memory in both directions. Whereas, for example, in this case, the interaction is unidirectional, and so on, right? And there is a particular order in which these boxes are put. So here is another example of Baddeley's working memory model. And again, you will see a set of processes represented by certain boxes and various kinds of arrows that connect them. So the question is, what exactly this mean, and how we actually get here, right? That's the general issue. To understand what cognitive science or cognitive psychology is, one way you can think about it is that the attempt here to study a complex system like mind is that you can actually have an understanding of how the mind works at 3 different levels. This comes from David Marr, and the 3 levels are computational level, algorithmic level, and implementational level. So computational level is essentially about computation, what kind of computation happen in the context of a particular process. At the algorithmic level, you can say, how this computation is realized using a particular algorithm. And at the implementation level, you can ask questions like, for example, how in the brain that this happens. So to study a particular process or a set of processes, you can address questions at all 3 different levels. They may be, to some extent, independent of each other. They may be dependent on each other, or you can try to use one level to constrain another level. But it's also possible you can study them to some extent independent of each level. Now, psychologists, for example, normally will not bother about the implementational level, but would very much worry about the computational level and the algorithmic level. I will exactly tell what it means, because this is critical to understand if you're a psychologist and you want to use the information processing approach. Here is a simple example from Steve Palmer's book. What it shows is an example of a thermostat. So what is a thermostat? All of your ACs and all, for example, have a thermostat. You actually have some kind of a temperature setting, which you set 25 degrees. There is an ambient temperature that this system measures, which is shown by a temperature here. And these 2 things are the input to the thermostat. And there is an output. So for example, in this case, signal to a furnace or signal to something that blows cool air or whatever it may be the case, right? So there are 2 inputs, 1 output, and then a particular way you can conceptualize it is, let us say that in this case, this is a heater. So that's why the word furnace is there. The thermostat checks as a setting. In this example, the setting is at 20 degrees. If the temperature that is measured is below 20 degrees, the furnace is switched on. If the temperature is above 20 degrees, then the furnace is off. Now, you can actually draw a diagram and show this input-output relationship. In this case, this is shown as a figure. You can also write it in a mathematical form. And let me see. And this is one way you can write this very simple example. Of course, real mental processes would be much more complicated. But the idea is that now I have expressed mathematically the relationship between input and output. And this quantified relationship essentially is what you mean when we say that we understand a particular process at the computational level. The next level is the algorithmic level. It's the same computation, but you can actually think of it as writing a program. You can write a program in many different ways. Here is an example. You have a temperature, and that information has to be encoded, which is shown here. You have a setting which you have done, which has to be encoded. You compare the two. So this block is a comparator. And then there is a decision, yes or no, and then ultimately this happens. Now, this is a very simple algorithm. You can have very complex algorithms depending on the computational function that you want to realize. But the basic idea is you can then break this computation into these boxes and arrows, which essentially, remember, we saw with the Atkinson-Shiffrin model and all that. And then we can say that these processes, interact with each other in a certain way. For example, the output of something becomes the input of something else, and so on. Now, we will talk about exactly what do we mean by input and output from a conceptual point of view later. You can also implement an actual thermostat, which you may have in a heater. And then here is a sample example circuit. This is an electromechanical circuit, but you can think of it as a brain circuit or whatever it may be. So in this case, this particular circuit has a battery. There is a metallic strip. If the temperature increases or decreases, then what happens is that if the temperature decreases, then this goes and this touches this setting. Once it touches, there is a way the current can flow, and then the furnace will get switched on. I mean, in this case, this is a fairly simple example again. So this is the way it's implemented. Now, you can implement it in many ways. This is just one way that you can implement. So what's the basic take-home message here? So you have three things: a computation, an algorithm, and some kind of an implementation, a hardware. So the main point to note is that these things are not one-to-one related to each other. So the same computation, if there is a particular computation, you can perform it using many different algorithms. So even if I tell you what the computation is, you would not know what exactly the algorithm is. There could be any number of algorithms that one can use. So that needs to be elucidated by studying, doing empirical work. Similarly, even if you find a particular algorithm and think this works in a particular way, like the memory model that we saw, then it can be implemented using different hardware in very different ways. And again, two different sets of hardware can implement or realize the same algorithm in different ways. So the important point to note is that there is no, just because you find something at one level, it's not that what happens at the other levels are fixed. They could vary quite a bit. Now, when you start doing cognitive psychology as a researcher, there are a few terminologies that one needs to understand. The first thing is we generally give what we call an informational description, right? So the information processing approach, that's the reason why it's called information processing approach, is that you give an informational description of what happens, basically mainly at the computational level and to some extent at the algorithmic level. The second thing you do is that once you have a particular process, you can break it down further, right? So this is what we do. So you can start with, for example, a box called memory. And then you can now break it into, say, three boxes, sensory memory, short-term memory, and long-term memory, and so on. And further, they can be broken down. And this way of taking a process and then reducing it to a smaller sub-process is called recursive decomposition. Now, it makes certain assumptions that allows it to, for us to be possible to do this. I mean, if somebody asks, what is the guarantee that our mind works this way, is that we can do this? The answer is, of course, we really don't to some extent. But we generally assume, if not strong modularity, but at least to some extent of weak modularity. That is, it is possible to take the mind and then decompose it into certain constituent processes. And this is a fundamental assumption that we make. And you can ask the simple question, how far we go? The answer is, of course, we can go to a point where these boxes become so small, they become a primitive that you cannot break it further, like an atom or something, although atoms can be broken down as well. But something like that. And that's the notion of a primitive. But you keep breaking into smaller and smaller or simpler and simpler processes. And when you do this, the most important aspect is that, and that is called physical embodiment. So if you have a physical system and you are describing its behavior as informational events, some kind of informational event, then you need to specify or worry about two things. One, the information itself is carried by certain states of the system. So generally we call that representations. So when we say a particular representation, that's essentially a state that carries some information. So we talk of representations in cognitive psychology or cognitive science. In fact, we try to find out what are the representations. Essentially in those boxes and arrows that you saw, those are usually the inputs and the outputs of a particular box. In information processing approach, they will be representations. So we can ask what kind of representations are essentially inputted to a system, what kind of representations constitute the output of a system. And the box itself, what it does is transforms a representation into another representation. And that is what, when we say a process or a cognitive process or even a mental process, according to this approach, this is what we mean. It's actually a process, a method that transforms one representation into another representation, okay? This may sound abstract to some of you, especially if you are not familiar with this, but whatever you read in cognitive psychology, it's actually essentially based on this kind of abstraction. So just to give an example about representations, you can think of representations in a simple way, that there is a world out there, and that is represented by, as you can see here, a particular represented world. Then there is the representing world. And this is essentially, you're thinking of as mind. If you have a bunch of states in the world, in this at least diagram, there is a corresponding representation in this representing world in your mind, and they are connected to each other. There is a relationship. So if, for example, these two states are related in a particular way, then these two representations would also be related in the same way. And if that happens, then we would call it as a homomorphism. That essentially is a mapping between two sets. And just to give an example, even if you have a particular world, in this case, it's a very simple world of rectangular blocks, which has two properties, height and weight. There is height and there is, width, excuse me. And you can represent, for example, the tallness or the height by these lines, which essentially is how long they are. Now, this is a way you can represent one aspect of this world. Similarly, you can represent the width exactly using the same property longer than, but you can see now the lines look a bit different. You can also represent using neuronal firings in terms of spike rates. So there are more spikes here and less spikes here. Or you can have more abstract representational structures. These are essentially graphs and a simple chain. So representations have, and you put a bunch of them together, actually have a structure. So we can try to find out what kind of a structure these representations have. And that is, again, part of the enterprise of cognitive psychology. So that's the first part. Now the question is, exactly how do we do this? Obviously, we do experiments in the lab. How do we actually get there? What kind of methodological tools that we have that we can use with some assumptions, and they may be right or wrong. We need to see that, and we will see some assumptions, and we also know that there are some problems associated with them. So historically, for example, going back to the 19th century, and this is the subtraction method that came from Donders, you can start asking simple questions like, how long does a process take? I want to find out how much time does a process take. Or how are these processes organized, how they are put together. And a standard method that is used in cognitive psychology is the so-called additive factors method by Saul Sternberg, that came out in the 1960s. And you can also tease apart specific characteristics of a particular process by actually doing specific manipulations. So for example, you want to find out whether a particular process is influenced by attention, then you may want to use, say, a dual task as a method to see whether a particular process that you are studying is actually affected by attention or not affected by attention. This is just one example, but there are many. So let's just quickly go over them. So the subtraction method simply says that if you have a time between the presentation of a stimulus and a response, there are a bunch of stages that happen. Now, if I experimentally do something, either add a stage or subtract a stage, have one stage less or one stage more, then I measure the time. Then I can take the difference between the two, and that will give me some idea of how much time a particular process takes place. So of course, like any other methodology, it needs certain assumptions, and these assumptions are listed here. It's important to know the assumptions and their limitations as well. So for example, you assume the total time taken for somebody to respond is the sum of all the times taken for individual processes or stages. These stages are independent of each other. They are not interacting with each other. If they interact with each other, then you can't apply this method. It's possible to add and subtract because they are independent. And this general assumption is called the assumption of pure insertion. You can actually insert something or take something out without affecting the other stages. Now we know this is a very commonly used method, but we also know, as various cognitive psychologists shown, that this particular method also fails in many cases. So just to see an example here, and this comes from Donders, 19th century. So you see that there is a stimulus, there is a mental event, let's call it perception, and there is a behavioral response. Now you are adding another stage here. In this case, let's call it decision making. Obviously, when you add some kind of a decision-making process, assuming the rest of them remain the same, and if, for example, you find out the time taken for this, the time taken for this, then if I subtract, then I know how much time is taken for this. So that's essentially the basic idea. More important, I think, are the additive factors method. So here the idea is, let's say you postulate a process. You want to know all the factors that influence this particular process, okay? So let us say there are two or more factors within the same task. If they interact with each other, right, then what does it mean? It will actually affect the same stage of processing. However, if they are additive, that is, if they do not interact with each other, this is statistical independence, then you can conclude that they actually affect separate stages of processing. So you manipulate, let us say, X and Y. If they affect a particular stage, then there will be an interaction effect. If you do, say, analysis of variance. And then if they don't interact with each other, then you will simply have, say, two main effects. There won't be an interaction effect. So now you can actually hypothesize, depending on the theory you have, if you think that these two factors affect the same stage or same stage of processing, then you would actually predict an interaction effect in your experiment. If you think actually they don't interact with each other, then you will actually predict there will not be an interaction effect. This is the way you will actually do hypothesis testing. So in this case, of course, you can't, unlike the previous case, you can't find out how much time and all that, but you can put them in boxes and then organize them in certain ways and also indicate what kinds of things affect these boxes. So here is a simple example that I have taken from internet. Imagine that you ask people to read words aloud. You ask people to read words aloud. You manipulate stimulus quality, how the clarity of the stimulus. You also manipulated, say, word frequency. That is how often this particular word is encountered in a linguistic community. Now, here are the results. At least this is a hypothetical result. But all you see is time is measured. In this case, this is low frequency. When it's clear, it's 550. When it's degraded, it's 650. And then when it's high frequency, it's 500, 600. Immediately, even without doing stats and assuming that the errors are not high, I mean, the standard errors are low, you can see the standard deviation here. Then you can see that the difference between these two conditions is 100. The difference between these two conditions is 50. That means there is actually an interaction effect. So you will conclude that stimulus quality and, sorry, I focused on the wrong side. I'll tell the other one. So the difference between these two is 50. The difference between these two 50. So the effect of frequency is the same for both clear and degraded stimulus. Hence, you will say that, well, they affect different processing stages. You may put like this. Or you can say in this arbitrary example, you can manipulate stimulus quality and repetition, say whether or not the word occurs more than once. And then you will get something like this. Now you can see even much more clearly that, so for example, this difference is 100, this is 50, this difference is 150, this difference is 100. They are not the same at all. And actually you have an interaction effect. So in this case, you'll conclude stimulus quality and repetition affect the same stage of processing. So this is the way you actually construct, by doing experiments and by seeing how these factors interact or do not interact with each other, you essentially construct a model. Of course, you can also then model it in very specific ways using equations, and then you can actually simulate it as well, which allows you to more precisely say what's happening. So this is now just to kind of two examples. You have stage 1, stage 2. We do not know what the names of those stages are. We have not named them here, but we know that stimulus quality and repetition affect the same stage. Word frequency affects a different stage. Now you have some kind of a building block that you can further develop as you go with research. Here also you make assumptions that the RT is a sum of individual stage RTs, and the stage durations are independent, and so on. And of course, insofar as these assumptions are not violated in a particular situations, then you will get results that will be decent, and you will get a decent model out of it. Of course, if these assumptions are violated, then there will be problems as well. Okay, I am kind of moving into a more specific domain. I'll talk about attention and consciousness, which is one of the things I study. But if there are any questions, I can answer them as well, because up to this is more general methodology.
Sir, we shall take questions at the end of the session.
Okay, fine. Thank you. So I'm interested in attention, and this is one of the famous old quotes from William James' Principles of Psychology. That was published, interestingly, in the 19th century. So for those of you who have not read William James' book, I strongly recommend it. It still is very meaningful, and probably much better than many of the recent books. So James wrote in his chapter on attention that everyone knows what attention is. It is the taking possession of the mind in clear and vivid form of one out of what seems several simultaneously possible objects or trains of thought. Focalization, concentration of consciousness or of its essence. It implies withdrawal from some other things in order to deal effectively with others, and is a condition which has the real opposite in the confused scatterbrain state. Now, there are a few terminologies here, words here, we need to focus on. So there is the word focalization, there is the word consciousness mentioned, there is something about withdrawal and selecting certain kinds of things. So what it implies is that there is some kind of a selection process, and all of this is something to do with consciousness. Exactly what, of course, we will see as we go along. So if you are interested in something like attention, and I do not know how many of you are interested in something like it, it plays a huge and important role on pretty much everything you do. If you are a teacher, and if you have students in your class, then I'm sure you have noticed that sometimes they pay attention, sometimes they don't, and you can tell by looking at their faces, perhaps. And attention is important for pretty much a significant number of activities that we do. So generally, we start with a very basic question: how does attention work? You can also ask further questions. Can we pay attention to more than one thing at a time? How are attention and perception, especially conscious perception, related to each other? Okay. So the main thing, as I said, is selection. So there is this notion that you select something, some information, or from the environment. Then obviously there are distractions. You need to exclude those distractions so that you can focus on the task at your hand. So there is this notion of, keeping the distractions out, right? And basically we think of selection as the process of focusing on specific objects. This is in the context of visual attention, which is what I'm going to focus on. You can be modality specific, or of course you can also conceptualize it in a non-modality specific central way as well. So you can focus on specific objects or locations and so on. The moment you say selection, then immediately you can ask further questions. So two simple questions immediately come to mind. One is, you can say, well, if I'm selecting something, I need to have a basis, right? If I'm selecting a student for my program, I need a basis to select this particular student rather than that particular student. Similarly, here, there has to be a basis of selection. The second important thing to ask is, now that you have selected something over some other thing, there is a consequence of selection. So what exactly is the consequence of selecting something over some other thing? So two questions you can study if you are interested in selective attention. One is the basis of selection. The other is the consequences of selection. Now, there are multiple ways you can ask these questions, and then you can classify basic theoretical positions which you may have seen in a cognitive psychology textbook. Here is one way of doing it. Some of you may have read in a basic cognitive psychology textbook about early selection versus late selection theories of attention. But this one actually parses positions about selective attention in terms of 4 possibilities, okay? Based on your answer to 2 presumably independent questions. One question you can ask is, if you do not pay attention to a particular stimulus, do you think you will be able to identify or consciously perceive that stimulus, or unattended stimuli identify? The second question you can ask is, can I actually process more than one attended stimuli? Now, your answers for both could be yes. So you can say yes for this. And you can say that, yeah, I can process more than one item in parallel, and that would be late selection. You can say no here, and then you can say you actually process only one item at a time, only one item that you attend to, and that will be early selection. But interestingly, the way you put this, you have two other possibilities. This is, you say yes, and you still say serial. And this is called uncontrolled serial, which is the least important position for now. Actually speaking, the more important position, and I think the position that has the most evidence, and sometimes it's not reflected in basic psychology books, is for controlled parallel. That is, if you do not pay attention to any stimulus, you don't consciously identify it, but you can actually process more than one object or one item at a time. Not a lot. It's not that you can process 1 million items at a time, and that's essentially the word control means. Maybe 4 items at a time, or some number like that. Now, the other way you can conceptualize, and there are many ways you can conceptualize attention, and one way you can conceptualize attention in terms of load. So you can think of it as high cognitive load and low cognitive load. And you can actually predict certain interesting effects depending on this notion of selection processes occurring differently when it's high load, and selection processes work differently when it is low load. And the basic idea, which was proposed by Millie Levy, is that if you have higher cognitive load, it reduces your ability to suppress irrelevant stimuli, or you could say something like that. I'm sorry, there is a typo here. It's lower cognitive load reduces your ability to suppress irrelevant stimuli. Exactly how do we do it? Well, you can use a particular task. This is a flanker task. You can think of an arrow pointing one way and arrows pointing in other directions, which operate as flankers. You're supposed to report the arrows. Or here is another task which is done with letters. So you have a bunch of 6 letters here. The targets are X or N in this example. And then you have an X, and X and N are the 2 targets, and there is an N that appears here. Now remember, this is a low cognitive load task because the distractors, these 5 things which are in this array, are homogeneous. They are the same, which makes it easier for you to identify the X and report it. In this case, all these 6 letters are different from each other, and in that case, it makes it more difficult for you to identify this X. And of course, this N is the distractor. You're not supposed to say N. That's a wrong answer. But it slows you down. Now, the interesting question is what happens in the context of this is low load and this is high load. And you can see the results here. You actually get a larger interference effect when you operate with the low load conditions. So actually, this theory predicts somewhat counterintuitively that if you are doing an easy task, you are more prone to be influenced by a distractor compared to when you are doing a much more difficult task. Okay, so the idea here is that you do an easy task, there are lots of resources left, and these resources are utilized to process or to identify the distractor, which actually means you end up with a larger distractor interference in actually the low load, the easy condition, not the difficult condition. So the distractor interference is more in the easy condition, low load, compared to the high load. This is another way that you can see that you can actually make slightly counterintuitive predictions depending on how you theorize and how you can parse and study specific processes and how they interact with each other. Here is another example. This is not a lab experiment, but you may find it funny. So there are 6 cards here. I want all of you to pick one card. It can be any one of these cards. Okay, focus on that card that you have chosen. If you have done it, I will move. Now I have shuffled, this is just a program. I have just shuffled all the cards and I have removed the one which I think was your card. Okay, I can do this magic. I don't know which one you picked. Now, can you still remember your card that you have chosen? I hope you can remember that card. Okay, so maybe somebody can answer. Dharmendra can answer this. Okay. So here are the remaining 5 cards. Is your card there, Dharmendra?
Second one, sir.
No, then you are actually forgotten what you have chosen.
All card most probably
No.
all card are replaced. Sir.
Yeah. So the idea is that, I mean, that's the thing, is that none of the 6 is here. So actually in any of them, but I don't know how many of you actually noticed that, right? Most people do not notice this. And the idea is that you don't pay attention to all the cards. You remembered pretty much, or you paid attention to only one of them and you try to remember that. And then you see that one is missing here. And essentially this is a form of inattentional blindness, that if you do not pay attention, then you do not perceive it. The other thing that can happen is that if you do not pay attention to changes that happen in your environment, that sometimes then you don't perceive them as well. So that is called change blindness. And there are various forms of change blindness that people have shown both in lab and in real life as well. There are some cute, nice real life videos out there in the internet. But let's see an example. So here is a particular paradigm, and let me just explain this paradigm because I'm going to give an example of this. So what you do is you show one scene. Then in the next scene, after a small gap, there is one change. Then the original scene comes again, then the change scene, the original scene, change scene, and it keeps repeating. Now, what you are supposed to do is find out what is the change. Okay, pretty simple. So maybe I will ask Dr. Ashwini Kumar to answer this question. So here is a picture here. There is a scene, you see, there's something changing here.
Yes, sir. Actually, I have gone through all these things, sir. Therefore, I can notice here.
I know, but it's okay. You can tell. It's fine.
It's Indian, sir. It's Indian that is there, which is
that is
consistently.
So, so now in this particular example, it's the engine, and some of you may have noticed it, some of you don't. And it's actually a bit of luck if you're doing it for the first time to notice it. Sometimes it takes for a long time. So the idea is that because it's flickering, it makes it difficult for you to pay attention. And that's the reason, or at least one of the potential reasons you miss or you're not able to detect the change. This is one way, but then there are other phenomena that I've shown that there are other things that happen. So here is a particular phenomenon called attentional blink. It is something that we commonly study in the lab. Now, in this case, stimuli are presented in rapid succession, one after another. So you see a bunch of numbers and letters here in this case, and you are supposed to report. And generally speaking, let's say there are 2 targets, T1 and T2. You can have only one target, which is a single target condition. There is only T1, or you can also have T2 as well. Now, this is the basic idea, right? And these things are flashing pretty quickly. That is, every frame takes on an average, including the gap, around 100 milliseconds. So in 1 second, there will be 10 such things that flash on the screen. So what you find is that if there is only one target, you are able to identify it with fairly good accuracy, 90%, 95%, no problem. So it's not like it's flashing fast and that you cannot do it. However, see what happens to the second target. If the second target appears a bit immediately, that is within 200 milliseconds of the first target, your detection performance is very poor. Usually, well, in this example, it's around 50% a chance, or it's sometimes we get even poorer percentages in some of the experiments that we have done, depending on the stimulus or the task that we use. So for example, we have done this study with emotional faces. I have not put that in. But if people are interested, I can talk about it, where the targets are happy faces or angry faces and so on. And you get different patterns. But the basic idea is that if two things happen in succession, and if you pay attention to something, it takes some amount of time for you to shift your attention to something else. And because of that, put it in a more simplistic way, there are more complicated models of this in the literature. You are not able, and this to detect the second target, and this is called attentional blink. This is just to give you some idea of some phenomena that people study in the context of attention. Now, I'm going to focus on, in the next 20 minutes or so, on some specific research that I have done and questions that I have asked. The first question, which at least in this presentation I'm going to talk about, is we all know, it's fairly trivial to see, that attention improves behavioral performance. Your accuracy, your response time, it's not that complicated to show. And people have shown it for 100 years or more than 100 years. More interesting question for somebody who is interested in consciousness or conscious experience like me is, does it change what you see itself? Not just how fast you respond to it or how accurate you are, but in a sense, the way you experience that stimulus, is that itself changes depending on the way that you pay attention or you don't pay attention to something. Now, if you go back in history of psychology, people had in the 19th century different views. So for example, Wilhelm Wundt, you can see the quote, thought that if you pay attention to a particular stimulus, it becomes more intense. Fechner thought that actually speaking, the qualitatively your experience doesn't change at all, whether you pay attention or not. And that's what Fechner thought. And James thought, well, it's a kind of slightly different position. It becomes intense, but there is a compensatory mechanism that nullifies the effect. Now, this is 19th century. We come to 21st century. Marisa Carrasco and colleagues at New York University showed that, well, actually you can use cueing, cues, which are exogenous, that is certain stimuli that flash on the screen, and using an orthogonal task that is a kind of where you have to answer a question that is different from what is being manipulated, show that your experience changes. So in this case, I don't know how well you can see this, but there are two dots here, which are the dots are the cues. And there are these, I don't know how well you can see this, I hope you can, these Gabor patches, which are just gratings, stripes, okay? And using these kind of stimuli, she showed, sorry, and these are psychometric functions. I hope all of you know how psychophysics works. You actually vary a particular variable on the x-axis. On the y-axis, you get a perceptual judgment. Then you plot, then you get a curve like this, what we call mathematically a sigmoidal function. And we actually fit this result with a sigmoidal function, and we can extract some parameters. For example, this 50% point, which is called the point of subjective equality. This is the point at which, let's say there are two possibilities, they are equal. So what you see in this thing, the only message, you don't need to bother about everything in this graph, is that if there is a cue at a particular location, and then a stimulus comes at the same location following the cue, your psychometric function shifts to the left. That means in this case, these are stripes with contrast. That is, some are high contrast, some are low contrast. And what actually happens if you pay attention to using a cue into that particular location, then it actually appears to have more contrast, in a sense, more clear. This is what she showed. What we did is to kind of expand it to look at one particular aspect that is very important for us, that is emotional expression. So when we perceive somebody is happy or somebody is sad, we also have this feeling somebody is really happy or really sad, depending on the emotional intensity they show in their face. Now, sometimes you may pay attention to that face, sometimes you may not pay attention to that face. So if that is the case, then the perceived emotional intensity itself should change if this argument that attention alters the way stimuli appear is correct. So which is what we tried. Using a very similar paradigm, there are dots or the cues that came either on the left side or the right side. You have these two rectangles, which you see here, and there are two faces that appear simultaneously for a very brief period of time. One is a bit above the other, and we essentially ask subjects, report the location of one of the two faces, whichever you think is, say, happier or sadder. We used a bunch of faces where we used multi-dimensional scaling to actually have equally spaced levels of intensity. Okay, so you can use the psychophysical procedure and then construct this stimulus set. And then you actually get a range of, so if you, the only thing you may notice here, I know it may be slightly difficult to see here, this is mildly happy, and I'm sure all of you can notice this is much more happier. And there are some intermediate levels of happiness expressed by this face, or sadness, and so on. This was done by my student Maruti Mishra. And basically we find the same effect like Marisa Carrasco, that if you are cued to a particular location and if a happy face appears at that location, then that face actually appears to be happier or sadder compared to essentially what it appeared in the uncued location. So to kind of give the broad point is that if you pay attention to something, it changes the way it appears to you. So that is essentially what these experiments show. You can also show that depending on how you manipulate attention in certain ways, here, this is a particular thing that I'm interested in called scope of attention. That is, sometimes you can zoom in and focus on some detail. Think of as focusing on the trees. Or sometimes you can zoom out and look at the forest, right? The big picture. So you can zoom in or zoom out. And one way you can study this is by either changing the size of the stimulus or by using what we call hierarchical stimulus, a large letter made up of small letters. The good thing about such a stimulus is that you can ask people to focus on the small letter or you can ask people to focus on the large letter. And exactly the same stimulus can be used. You can either through instructions or through task demands manipulate this. And we did this. Essentially, all you see here is a blue square. And I'm sure many of you know, let me see whether it's there or not. No, it's not there. If you see a blue square, and then if we keep staring at it for, say, 30 seconds or 1 minute, you can try this in your computer monitor. And then you remove it, and you have a blank screen. Then what you will see is an yellow square. Even though there is no stimulus on the screen, you will see an yellow after image. Now, this is a very old phenomena going back to 19th century. Herring showed this. But interestingly, the way you pay attention, and that we manipulated by making people do some counting task with some letters or numbers at the center. And then we showed that if we change the nature of the task that we ask people to do at the center, the duration of this after image changes. So it is what is shown here. If the letter is small, the after image durations were longer. If the letter is local, it's a bit longer than global, and there is large. So remember though, depending on how your attention is manipulated or used in a particular task here, it actually influences what you visually perceive, in this case shown through an example of color after images. In addition to that, we have also shown, this has been shown by Amrind, is that we can also ask how clear the after images are. The after images are usually slightly blurry or fuzzy. So we can ask people to rate clarity of the after image, which is shown here. And you get, again, some kind of similar effects in the sense if people focus their attention with, say, the small letter, then the clarity of the after image is more compared to when it's a small letter and so on. And interestingly enough, we also get effects or differences, which is also in this graph. One of the things that I study are effects due to the practice of meditation. So I have put some of that here. because meditation practice involves manipulating attention one way or another, you would expect if meditation practice changes attention and attention influences certain things, then meditation process would affect those things. So you can actually have some kind of a hypothesis like that. And we find that after meditators have longer after image durations, much longer compared to, if you see the values here, you will see much longer compared to, I mean, this is for meditators, this is for non-meditators, and you can see it's a huge difference. And you also find differences in clarity. So for meditators, the after images are much more clearer or sharper than non-meditators. There are other ways we can study this and interesting phenomena. And here is another example. Okay, so here is a Necker cube. This Necker cube is a cube, and if you keep staring at this Necker cube, you will see that the cube looks in one direction. If you keep staring at it, and I hope you can do that now, it will flip. You will now see the cube in a different orientation. And this changes every 3-4 seconds, and it keeps happening. This is what we call bistability. That is, even though the stimulus is not changing, what you perceive keeps on changing due to various intrinsic or attentional processes that happen in the system. Now, again, you can study this process through instruction. So we can ask people to control this. So I can ask a normal person like you and ask you to control this. So for example, I can ask you to hold one particular interpretation as long as possible. It will change eventually, but try to hold it. Or I can ask you to, oh, no, don't try to hold it. Try to change it as fast as possible. And this is what we call endogenous control. That is essentially trying to control what you see through instruction. Of course, in normal stimuli in real life, it's difficult to do because there is no ambiguity. However, this is a nice lab stimuli where there is ambiguity and bistability. So we can actually do this. And we can also do it with meditators. So let's take the simple neutral viewing condition. Meditators generally see a particular orientation for longer durations. Essentially, people simply have to press a key and report when there is a switch in their perceptual experience. And you find meditators have longer, what you call dwell times or switch durations. Interestingly, there is a much bigger difference here that meditators are able to hold a particular point of view for much longer period of time. There is not much difference in the case of switching because actually you can't go much below that. There is a kind of a floor effect here. So we can't say too much about it. But in this case, there is no difference. And what we normally do is that because you get various times, and this is actually a series of times, you can actually plot a distribution, a probability distribution. You have dwell times, and then a probability density function can be plotted. And you can actually fit it with a particular function, the actual nature of the function you can see here. But you can extract certain parameters, and they tell you certain things. So for example, you can get a parameter that is sensitive to shape, sensitive to theta, and you can show that as you change your control, these parameters change. That's the idea of, or strength of, using some quantifiable equations and modeling. You can actually then exactly say which parameter is influenced by this. You can also use flankers. So here is an ambiguous Necker cube here, and you have these flankers which flank. There are two possibilities shown here. Again, you can do it with meditators and non-meditators. You can see with non-meditators when the flankers are same, in the sense they have the same orientation, then your times are longer. It somehow benefits you. The flanking information is similar, so it gives you a beneficial effect, so you see it for longer period of time, compared to when the flankers are incongruent. It's a bit like a Stroop effect, right? Interestingly, with meditators do not show this. They are essentially able to focus on the central stimulus so well. The nature of the flankers does not matter here, and you can see this in the distribution as well, not just the mean value. You can see the distribution for both conditions for the meditators are completely aligned. So this is another thing. Instead of just plotting the mean, which of course you can do, you can actually do more with that, with your data. You can actually plot distributions, and you can actually extract much more information than simply calculating the mean or the median, okay? Even though they are important, most important parameters. Okay, so let me speed up. So far we have been talking about visual experience, but it is not just the case that we study visual experience, we also study, or at least I study, time. So I'm interested in how we perceive time and how our experience of time changes depending on what we do. In the context of attention, can we manipulate attention in specific ways and then show that your experience of time changes as a function of the way that you pay attention to something? Again, here we are looking at scope of attention using these big letter stimuli made up of small letters. And what you see here, the only thing I want to see here, again, you see a psychometric function. And what you see is that the blue is when you are focusing, paying attention to the large letters, the so-called global level. And you can see that function is much more steeper. So for those of you who have already done some psychophysics, this slope measure is a measure of just noticeable difference, right? What is the just noticeable difference if in the case of perception? So what you see here is that in the context of global, your temporal resolution increases, your just noticeable difference decreases, compared to when you are paying attention to the local level. So here is another case where we show, and this is just one example, that depending on how you pay attention, it changes the way you experience time. Okay, so this is something I've already seen. I had put that demo, but I will skip. I had shown this already, so let me skip this and move on because we need to answer question. Here is another example of effect of meditation, which I thought I will put. Here is an attentional network task. And in this attentional network task, you have 3 kinds of conditions. The nice thing about this task is that you can measure 3 different attentional processes: alerting, orienting, and conflict monitoring, using the same task. So what you see here is there is a fixation point. Sometimes the cues appear. These 2 stars are 2 cues, top and bottom. This is a double cue condition. Or there is a single cue, or there is a single spatial cue. That means that if the star appears here, that stimuli will appear here. And what you have is you're supposed to do is this is a flanker task. You're supposed to report the direction of the central arrow, pointing this way or pointing this way. And you can see in the congruent condition, all the arrows are pointing in the same direction. In the incongruent condition, they are not. Well, the basic idea is in the incongruent condition, people will be slower than in the congruent condition, like the Stroop effect. And that is what you get. But the interesting question is what happens due to practice of meditation. This particular study was done with adolescent children in Allahabad. And then you see that the practice of, in this case, transcendental meditation, changed the way these kids, so the meditating children showed a larger alerting effect, which is what is shown here. A larger, or a better alerting effect, which is shown as smaller score here. That is shown here with meditators here. And similarly, better conflict monitoring, which is shown as a smaller error bar here, a smaller effect here, which means the flanker doesn't affect you that much. So, which we saw in with adult meditators with the Necker cube as well. So again, you see specifically. Now, interestingly, in this particular meditation and this particular group, we did not get any difference in orienting. So it is not always the case that all types of meditation have same effects, or they will give you same effects for all processes, even the same type of meditation. So some may get better, some may not, and one needs to study them. Okay, thank you. I think I will stop here and take questions. I think I'm almost on time. Okay.
Thank you, sir. Thank you so much for an edifying and illuminating session. I would like to take 3 questions from the participants. Sir, we have question from Mr. Harshit, and he has asked, remember happy things, forgetting of painful. How can we explain this statement, sir?
Can you repeat that question, please?
Yes, sir. So he has asked how can we explain this fact that we remember the happy things and forget the painful one?
That's not, it's not as simple as that, right? So now there are there are multiple factors that influence our remembering. So one of the things, for example, is intensity. So obviously, if you have a mildly happy event and a very, very bad negative event, think of it as very highly intense negative event. So obviously, you will remember it. So this question, one has to be a bit careful. So it's not always the case that balance is the only factor that affects this. Having said that, there is some evidence though, and there are reasons for it. One of the reasons, or at least that I have studied, so let me throw that as a possibility, is that so if you have emotional information, there is some evidence emotional information and attentional processes interact with each other. So unlike what some of you may have told you, that our attentional processes clearly depend upon, now I think it's pretty much well established, on the kind of emotions that you have. Okay, so one of the things that people have noticed is that if you are happy, then your attention, remember we talked about zooming in and zooming out. So if you are happy, or if I show you a happy stimulus, your attention kind of zooms out. And if it is the case that if if you are, say, a negative emotion, then attention is more focused. Now, this can lead to different effects depending on the situation. So sometimes it happens that by actually zooming out, you remember things better, or things lead to better performance. Not always though, because it also partially depends on the kind of detail about the emotional event that you are trying to recall. So some people have argued or shown that if, for example, you are trying to remember a very minute detail, then obviously if you are negative emotions, actually, you do better, especially if the minute detail you're trying to remember is also negative. The classic case in which happens in the case of a disorder is depression. So in the case of depression, people are able to think about every minute negative thing that have happened in their life. And that actually turns out to be very bad for them, right? They are not able to forget it. So what I'm saying is that even those things can fail as well. So because it's a negative event, so sometimes you focus on minute details, and you are able to remember minute details better. So there are multiple factors that people have studied, and one has to qualify the statement. So there are studies that support that, and then you can essentially argue give a valence-based explanation, and somehow the valence influences attention, and because it influences attention, you encode information differently, and because you encode information differently, you remember it better. So this is one way that you can, people, broad sense, try to explain what the person who asked the question mentioned. But as I said, I would add a caveat by saying that there are subtle effects that people have studied and showed that it depends on context, it depends on intensity, it depends on multiple other factors. Okay. Hope it makes sense.
Okay, sir. Sir, next question is attentional blink and change blindness often used for flip book, animations, or any other type of videography? How can this be applied?
Oh, well, people may use it. I mean, magicians use it all the time. So that's what they do, right? So if you are being to a magic show, obviously they are not making things disappear or whatever. It's actually magic, right? They actually don't do it. So magicians are one, from an entertainment perspective here, are people who have understood attention for a long period of time and have used essentially various attentional manipulations that we now have studied in the lab. They have been using it for a much longer period of time before we actually systematically started studying them. So the answer is yes, people do use them for whatever ways and means that one wants to use. You can, there are multiple factors that influence these things, which some of which we have studied ourselves. Yeah, the answer is yes. It can be used for real life applications or to study specific issues in patients and so on and so on, which people have done.
Yes, sir. Sir, next question we have from Dr. Saha. So he has asked, thus internal states such as trait anxiety can also modulate the impact of attention on early visual processing.
There is some evidence that it does. So we know that emotional information or emotional states, there is some evidence it can influence early visual processing. People have done both neural studies and psychophysics to show that. I can't quickly immediately recall a particular study with anxiety, but I know there has been a study that has been done with angry faces or fearful faces, for example. So essentially in this version, which I immediately remember and I will share, is that you can show, for example, a negative emotional face, let's say at a particular place on the screen. Immediately you ask people to do a very simple visual processing task, and you can show that there is a difference between if there is a negative emotional face compared to a positive emotional face or a neutral emotional face. This, for example, has been shown, and people have shown evidences in the brain in fairly early visual areas. I would think, although I can't recall a particular study offhand, my guess would be it's probably true for anxiety as well. That I think there is evidence that anxiety influences very early processing. Yeah.
All right, sir. Thank you, sir. Sir, next question we have regarding a book. So, sir, is there any book in the market available with regard to Fechner's psychophysics?
Oh, there are more than one. There are at least 2-3 textbooks on psychophysics. Just go to Amazon and type psychophysics, you will find them. Yeah, there are at least 3-4 books available.
Thank you, sir. Sir, the next question is, can attention be studied in an outside laboratory setting, for example, in an actual classroom?
The answer is yes. And the answer also is that we are not doing it enough. So for various reasons, so we have been focusing more on the lab, but there is more and more emphasis on studying attention in real life situations. Some of even the illusions like change blindness, for example, actually has been demonstrated in real life. So there is a cool video that in a university setting, if you see that there will be one person stopping a bystander and asking a question, then 2 people will take a door and then move in between those 2 people.
Yes,
and then the one person, now the person talking to changes to some other person, and people who actually are answering the question don't even notice this and continue telling the way to go to wherever. So it is not the case that just because we study these things in the lab, they do not occur in real life. They do occur in real life, number one. Number two, it is true that we should do more to study in real life. So for example, take an example of visual search. Now people have done visual search studies in the lab and have reasonably good models of it. But people have also studied visual search in specific settings. So for example, if you have gone through, I don't know, airport security, the security is watching what is inside your suitcase through some kind of an X-ray type image. The security is searching for a particular, let us say, a dangerous object. Or if you are a doctor, you have these medical images, and the doctor is searching for a particular kind of problem, like a tumor or something like that. So now these are all very specific domains where we employ visual search. And there are many papers now coming out with specific real-life examples of how you can study attention. So now there are mobile eye trackers available. So you can track your eyes as you are moving, say, for example, on a street. if you want to, or at least in a relatively controlled street environment, not in Delhi streets or whatever. But you can actually put that like a headgear, and then you can actually manipulate attention, and you can study, for example, where their gaze is, how they are paying attention to various parts of the street, and so on and so forth. You can also do intermediate way using driving simulators and all, but you can also do in real life as well. So the answer is yes. In addition, I would add that more of you will do it more compared to lab rats like me.
Thank you, sir. Sir, I'll take the last question for the day. Does perception affects the attention of a person?
Perception affect attention of a person. Well, the question is posed in not a very specific manner. So one has to say, what do you mean by perception and what do you mean by attention? But if there are certain aspects about attention or certain attentional processes that are definitely affected by what you perceive. Okay, so processes that think this way, attentional processes that occur after perception, and there are many of them, definitely would be influenced by your perception. So for example, one simple way you can think of it is that we have to select. Let us say we are in a particular situation. There are more than one action that you can do, right? You have to select. Here also it's a selection process, but this is selection for action. We have to select, do I perform this action or that action? Now, this obviously would depend on your perception. So there are cases in which very specifically certain attentional processes are influenced by what you perceive, especially what we call late selection processes. Situations in which early selection occurs, they, of course, where attention itself, as we have seen in some example, is needed for perception. So it is both are true if you put it in a very broad manner. Okay. But you can go more fine-grained than that as well.
Right. So, sir, if you permit, sir, if you permit, I'll just take one more question.
Sure.
Yeah, that is from Dr. Sanjay, and he has asked, sir, will you please point the situation or conditions where one can concentrate his mind?
One can concentrate?
His mind.
Well, so learn how to meditate. That's one way of doing it, which is the Indian time-honored tradition of training your attention. And it has very little, there is nothing like very little side effects, but it has less side effects. But I mean, people have shown that even if you play attention demanding games, for example, or any attention demanding task, that helps. So in some sense, basically it means you keep your mind active, do things, then your cognitive processes would get better in some broad general manner. But as I've shown, since I study meditation myself, meditation is one way that you can achieve that, even though it's a bit harder than some other methods.
Thank you so much, sir. I do have one small query, sir, if you allow, because we have already crossed our time.
No problem. You can ask the question.
Yeah. So my question is related with the Stroop task, sir. When we have a participants, those who are doing any meditation practices in their daily routine, does it has any effect on the Stroop interference, sir? It can be minimized, sir, at one extent. What you're taking this?
The answer is yes. People have already done that and shown.
Yeah.
This is published literature that you get lesser Stroop effect in general if you practice meditation, which we have got it shown it in the context of a flanker effect, which is the same mechanism possibly or share similar mechanisms. But in the specific context of Stroop, people have already shown that, yeah, it doesn't go to zero, perhaps, but it reduces significantly. Okay. But having said that, I also want to point out, even with normal people, you can manipulate certain parameters and reduce Stroop effect. So one simple thing people always forget is that if you have a block of trials then if you throw in more incongruent trials, then and less congruent trials, then Stroop effect will decrease. So people are sensitive to task demands. When both are equally probable, then the answer is yes. But you can reduce Stroop. Stroop effect is sensitive to many manipulations. For example, in this case, probability of occurrence. So you can reduce it, use even for normal people. But yeah, practice of meditation decreases Stroop interval.
Okay, sir, and it has the same significant effect in Stroop-like task effect as well.
Yes.
Like when. Okay. Yeah. Thank you so much, sir, for answering all these questions and so patiently. And I would say that it was a very enriching session for all of us, and it was a great opportunity for us to interact with you. You know, although it's a virtual mode, but it was very fortunate for us in the way, like in the refresher course, with the help of refresher course, we are interacting with you. Thank you so much for your time, sir,
and thanks to everybody who was patiently listening.
Nirupma, you may.
Thank you, sir. Sir, again, on behalf of all the participants and the organizing committee, Department of Applied Psychology, Ramanujan College, I express my heartfelt gratitude to you for accepting our invitation and for spending your valuable time with us. I read so many papers of yours with regard to meditation, and I was wondering maybe one day I'll meet sir. So I couldn't meet you personally, but yes, you're here, and I'm the luckiest one, I can say that. So, sir, thank you so much. Thank you so much.
Let's hope the COVID goes away soon and we can all meet in person.
Sure.
Thank you so much, sir.
Due to some technical reason, Tiwari sir has not joined us, and
no problem.
Thank you so much, sir, once again from organizing team and the Ramanujan College.
Thank you.
Thank you. Have a nice day, sir. Thank you.
All of you have a good night.